All right, so here we want to write radical expressions in simplest form. So we're going to start with an expression that has the radical symbol in it. And most likely when we're done, that radical symbol will still be there, but it will be simplified from what we started with, right? So of course there are several shortcuts if the bases match or if the exponents match, so long as the operations are just multiplication or division. Right, so here's an example of what we've been doing. We said, hey, if you got 7 to the second times 7 to the third, the base is matched, we can just do 2 plus 3 and get 5. It's 7 to the fifth power. If we have like 5 to the eighth over 5 to the second, we say, hey, the bases match. Simple enough, 8 subtract 2 is 6. Right, so again, if multiplication or division is involved, shortcuts are really nice and straightforward. But if we've got addition or subtraction, that's when things get a little bit slower. All right, so if I've got the cube root of 54 plus 5 times the cube root of 16, what do? I can't take the cube root of 54. I can't take the cube root of 16. So what can I do? We can only combine like terms. So I'm thinking factor tree time. All right, I'm thinking about making a factor tree because we can only combine like terms, so we need matching radicands. Right, so you want to impress all your friends, go walking around talking about, hey, I know what's inside this radicand, right? Right, it's the number inside the radical symbol, the radicand. Or maybe it won't impress your friends at all. So if I've got 54 and I want to simplify this, I'm thinking, okay, factor tree. 6 times 9 makes 54. I could have used a different pair of factors. I could have done 27 times 2. I could have done 18 times 3. But I just picked 2 factors. Neither factor is a prime number, so I continue. Right? 6 is 2 times 3. 9 is 3 times 3. All of those are prime numbers, so I can stop. 16 is inside the other radical symbol. I can start with 4 times 4, or I could have started with 2 times 8. Since 4 is not a prime number, it's composite, I can break that down into 2 times 2. And so I keep going the factor trees till all I have are prime numbers. I'm like, aha, 54 is secretly equal to 2 times 3 times 3 times 3. 16 is secretly equal to 2 times 2 times 2 times 2. Hey, cube root, right? Third root. Look at that. I can lasso 3 identical factors inside each radical. So if I can take the third root of 3, that becomes a plain old 3 out in front. Notice the 2 is still inside the radical symbol. I see 3 identical 2's, so the cube root of 2 times 2 times 2 is plain old 2. Notice there's one extra 2, which has to stay inside the radical symbol. And also notice that there was already a coefficient of 5. So I've actually got to do 2 times 5. Right? If I can take a cube root, I can put the digit out in front as a coefficient. And then of course, if there's a number that's left behind, that stays inside. And notice those match, right? 2 matches 2. So I've got like terms. 2 times 5 is 10, so I got to rewrite this. I've got 10 of those cube roots of 2 for the second term. And so finally, I know 3 plus 10 is 13. So like if I've got 3 dogs and 10 dogs, I got 13 dogs. If I got 3 pennies and 10 pennies, I've got 13 pennies. So if I've got 3 cube roots of 2 plus 10 cube roots of 2, I've got 13 cube roots of 2. Another example. Like, 20. Well, 20 can be 2 times 10. 2 is a prime number, so that stops. 10 is 2 times 5. Those are both prime numbers, so I'm done. So I've got 2 times 2 times 5 for 20. Now, if you're kind of observant at this point, you're like, hey, I'm going to get stuck with that 5. I bet I get stuck with a 5 on the other ones also. 245. So I'm going to try 5, and I'm going to have to grab a calculator and say, hey, calculator, what is 245 divided by 5? Calculator says 49. 49, of course, is 7 times 7. So I've got 5 times 7 times 7. 45, again, I'm thinking I want to stick with that 5 because it looks like that 5 is going to be the extra leftover number. 45 is 5 times 9. 9, of course, is 3 times 3. And, of course, square root, that's the same as the second root. So if I can pair up numbers, I can take it out. So sure enough, I've got a pair of 2s, and then I see a pair of 7s, and then I see a pair of 3s. So if I've got a pair of 2s inside a second root, I can take out a 2. If I see a pair of 7s inside a second root, I can take out a 7. If I see a pair of 3s inside a second root, it can come out as a 3. Right? Square root of 4 is 2. Square root of 49 is 7. Square root of 9 is 3. Right? That's why those can come out. Now, we already had some coefficients in front of those radical symbols. So I could go 2 times 6 to get 12. And I got to do 3 times 4 to get 12. So I've got 12 root 5 plus 7 root 5, which makes 19 root 5. And then subtract 12 root 5 leaves me the 7 root 5. Or you might just notice that the 12 root 5 and the negative 12 root 5 cancel out. Right? Either way, you should come up with 7 root 5. Right? So we got a beautiful sunset that we're going to ride off into as we practice this skill.